let's go to the last actual part. It's here. It's here. It's, let's see if I can remember the page number. Around here, maybe. Yes. So I'm jumping into the notes. That's as I did last time, and I do it again now similarly. Here is what we call a complete worked through example. This time it has to do with car tires. And there is also a reason for choosing this little example, because now we have been talking a lot about blocks being persons, right? So sometimes that is often the case, that blocks are persons. And that is many times used for examples because that's such a natural block in many settings. And then people get confused because maybe they didn't think about that. We could open that up a little bit in the way we talk about blocks and treatments. So here's another example. 3 different types of tires, which are called the treatments, are actually tested on 4 different cars, which are then here by the story defined as the blocks. So the main focus here are the comparison of the tires, right? But they are used on different cars that might also differ, right? How they are producing wear of the tires, or fuel economy is the issue here. So in this case, blocks are cars now, and in a way the table is sort of tilted or transposed. But that shouldn't kill us, I hope, as engineers, that sometimes blocks are in rows and at other times blocks comes in columns. So I think we can cope with that. Also because, I hope, I said it already, and from this it's also clear, actually, when it comes to the computations that we do, and when it comes to the statistics that we can do, the F-testing and the post hoc comparisons, this 2-way setting is completely symmetric in what we call treatment and what we call block. It's just in a way for historical reasons that something was called a treatment and another thing was called a block. But it's really just a 2-way table of 2 different things differing in a way. Could be 2 different treatments, actually. It would be a similar issue, which this might be. So it's just to remember, blocks can be different things. It doesn't have to be persons or something like that. In this case, blocks are cars, and the treatment are tires. So there are 3 by 4 numbers, and the means are already given to us here. Here we see how it is, how we are putting it into R. This is just the column of Y's, 4, 4, 4. The car factor. And here note how it's important to tell, that is also a repetition from last time, it's important to let R know that the coding 1, 2, 3, 4, 1, 2, 3, 4, that codes for cars, right? Because the numbers 22.5, 24.3, these are car 1, 2, 3, 4 for the same tire, right? So I'm making a coding. The car vector is the coding of what those observations really are, right? I'm telling R that the first 4 numbers, they are coming from car 1, 2, 3, 4, and then again 1, 2, 3, 4, and then again 1, 2, 3, 4. So I'm making this information about what these numbers are, what their position in the table is. I am telling R by these 2 vectors. I am using, because that's easy, in my sort of, when I work with that, it's easy for me to use 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, rather than A, B, C, which are different places on this thing that you write on. What's the name of that thing that you're writing on? The keyboard. Thank you, DER. That's what happens when you go beyond 50, right? Suddenly things are empty in there. It's not a nice feeling, but anyway. Then I make the car data set. I put those 3 columns in a data frame, and then I do some plotting. I think actually I plot like before versus tire and versus car, right? Let's see what it will give us. Gives us this. So this is the raw data plotting. Explorative data analysis. Nice start. I didn't do any fancy stuff. I'm just looking at the data. Seems like tire 1 is at the top. Tire 2 and 3. Lower, more or less the same. What about the cars? Well, definitely car 4 seems to be different from the other 4 cars. Should we just remember what the numbers really are? How much were we told here? Fuel economy, drives. So it doesn't tell us much, but why don't we speculate that these are actually how many kilometers per liter that we can... It does say? Kilometer per liter? Okay, thank you. It does say, so they are, as they always do in the car industry, looking very nice when you test them. So tire type 1 is the worst, right? Car 4 is the better one in terms of having good fuel economy, right? Multiply my statement by -1 here, right? I realized that before you kicked my ass there. Then now we do the analysis, right? I do the analysis. I run the ANOVA. I do the LM, as you've seen already. We're just having some visitors, don't worry. It's not serious. It's just visitors. I knew they were coming. We see the analysis of variance table, as we have seen already. We get all the information. The first thing I'm looking at would be these 2. You could have a question also at the exam. Some of them would be, you've seen them maybe. What's the story? What's the conclusion based on this data and based on this analysis? Are the tires different in terms of fuel economy? Yes or no? Yes, they are. Are the cars different? Yes, they are. Why do we say yes? Because those 2 p-values are less than 5%. Usually we are told to use 5% level. If no one tells you, actually R uses by default the 5% criterion. That's why it gave you a single star to tell you, remember our p-value evidence table from a long time ago? This is this 1-star evidence level. It's below 5%, but it's not extremely low, right? There is something, but not that high evidence. However, yeah, this is the nice tech version of the same thing. You can do that by X table in R if you are a combined LaTeX and R user. That's convenient. We are not quite done because I should have checked my model assumptions actually before I got too wild about the conclusions that I just shared. So actually, before dwelling too much on the conclusions, I should check the model assumptions. For instance, the normality assumption. Not by the Wally plot here. I like the Wally plot, but here's just a single plot. It looks nice. Look at the thing. I'm plotting the residuals that I extract from my fit object. I do what I showed you before again, like that. I plot the residuals now versus cars and tires. Here they are. Do we have approximately the same variability across cars and across tires? Wow, that's one of those cases, right? I mean, this one, definitely fine. No problem at all. This one, What would you do to be more safe here? The question is this variance really different from the other variance? Wouldn't you be able to compare variances by a statistical test? I don't remember my teacher taught me that. No, I didn't. But this is step one on your future, exploring the rest of the elephant, right? I told you how to do statistics on a single variance, but I didn't tell you how to do a statistic to compare two variances. But it's not difficult for you now. It's just an F test. You can Google it, and it's easy for you. You can do that test. I'm not going to check you on that test because it's not part of my syllabus, but it's very, very close to my syllabus, and by the same lines of thinking, you can do that yourself tomorrow. Then we could check whether it's really a problem or not here by statistical methods and not just by visual investigation. So that leaves me with the conclusion about these data. We still need the important thing. What about the post hoc story here? What's actually going on? The story about the tires, that's the core thing. That's the treatment factory. Well, we already saw the story on the box plot, but now I compute the means. Tire type 3 appears to be the one with the worst economy. Tire type 1 is the one with the best economy, right? Please stop me if I'm mixing things again. Question?
Is it vice versa? No, never mind. It's morning. Never mind.
It's difficult for me also, right? If you go, let me try again. If you go 23 kilometers per liter, you're doing good, right? I'm not sure that's what I said, but do we agree now that that's what we have as a conclusion here? Good. It is morning, yes. Then I refer to this LSD thing again and go to the chapter on one-way ANOVA to find the formula. The LSD is this thing where I can compare, where I can compute the confidence interval width to be used for all comparisons. I compare it once and for all. I compare it by the square root of MSEs and some factors, and then the T statistic. And please note that I use the Bonferroni correction because there are 6 comparisons. That's the capital M. So I do not use 5%. I use 5/6. That is a bit less than 1%. I find this measuring stick to be 2.53. That's the one I'm going to use. And let's see here the result. That's the final thing. Here's the result. Final conclusion of this data analysis. I use this 2.53 measuring stick and just checks which of the tires are different from which, right? Only 3 and 1 are different from each other because that difference is larger than 2.53. So I make the hypothesis test by that way, right? Whereas 2 and 3 are not different, 2 and 1 are not different, but 3 and 1 are different from each other. That's what I have found by these data, right? That's how it is. I mean, sometimes we have such a bit of overlap conclusion. That's real life. But we do know that there is a difference between 1 and 3. 1 being the nice one, right? Good. That's it. Now I'm going to test you. There you go. Usual place, Socrative, room, PBB. I have 2 questions for you, and I'm going to kill you if you don't answer them correctly this time. You may discuss with each other, that's not prohibited. I'll give you 1 more minute on this one, and then I have a second one for you. So 1 more minute, if you want to play. Okay, how did you do? Oh my goodness. Let's read the question. 1 and 2-way analysis of variance have as their main purpose to compare the variances within each group with each other. No! I've told you 25 times now. Even though the name may seem like that, because the name variance enters the name of the method, the purpose, the very simple-minded purpose of these tools today and last time is what we could have started already in 3rd grade. That is, I want to compare the means of my treatments, right? That's the purpose. I'm not being more complicated than that. The only reason why we have the variance in the name is because this is our way to compare the means by certain variances and not the variances within the groups. Those are not compared by the methods. They are supposed to be the same, as we discussed at the end, right? Okay. Next, and make me happy now. Actually, this is more difficult. Anyway. Have a chat about it, 3 minutes, and you're off for today. At least if you answer properly. While you finish your answering, let me just discuss my question with you. I'm discussing the situation that maybe I don't have many treatments, I only have 2 treatments. And then I'm thinking, hey, what is the link between this and my paired t-test a few weeks ago? Because that's like having a number of persons and 2 treatments. I could just take the difference maybe and look at all those. Is that the same? You look very questionable. Now he's tricking us again. Hey, I'm a very honest man and I would never trick you into anything. let's relieve you here. Yes, it is, exactly. And this is a nice link. I put the question just in case that I forgot to make that point, which I did, so it was good that I made the question. The point is, last time we did the completely randomized experiments as the natural generalization of the independent two-sample t-test, right? Not two groups, but multi-group independent samples, multi-independent samples. Now we have the natural generalization of the paired t-test, where we have paired or dependent samples. Now I have multiple paired, but that's the word paired doesn't make sense if I have more than two. So we call them blocked or dependent samples. It's the natural generalization of those two ideas. And both ideas are important for you as engineers out there. You may use both of those ideas in the future. The block thing is very nice to use when possible, but sometimes it's not possible. You only have one shot, and then you have to use completely randomized. We didn't discuss the word randomized, but that's the design part of it, the planning. When you plan such studies, it's very important that people are randomized to treatments. And when you have blocks, all of them get all treatments, but then you randomize the order in which they get the treatments. That is to take care of all of these other problems of selection that we've discussed previously. That's why people in medical clinical trials sometimes have to accept to get a treatment by lottery, right? You're asked whether you accept to enter a study, and you can say yes, and then the treatment you get is by lottery, by randomization. Because if you don't randomize, you don't know what the output will be. You cannot use your output for anything. So that's just the end. That's why we call it randomized experiments. We discussed how to analyze them. Now you're ready to do it out there. So enjoy the day and see you next week.